Hi, everybody. My name is Cedar Fox. Welcome to the UW Robotics Colloquium. It's really my great pleasure to introduce today's speaker, David Held. David is faculty at Carnegie Mellon University, and I've been following his work now for, let's say, close to a decade. I think the first paper that I saw of his was the RSS 2014 paper on where he did tracking from autonomous vehicles, tracking other pedestrians or bicycles, combining LiDAR information and visual information. So that was really nice because it also was kind of ahead of a lot of the other developments that were coming up after that. And it also nicely illustrates his kind of work where he is focusing on perception algorithms, but that have like really high relevance for practical applications. Later on, also, I really like the work, for example, on the kind of learning to track at 100 frames a second, because we were also at this time working on object pose tracking. And I really thought that was amazing, the kind of speed that they were able to achieve for tracking objects in videos and things like that. And overall, so David's background is coming, let's say, more from a computer vision perception side. But I think he really cares about bridging this gap between robotics and vision. So now he's kind of really solidly working in both of these areas, making really nice contributions to perception, but very much so in the context of robotics. And as we know, one of the big questions in this area is, of course, how do we even represent objects? Should we just learn to detect objects independent of a task, or can we do that in the context of specific tasks? And David's done some really nice work in that area and investigated these techniques also in really interesting domains such as like folding or modeling, cloth, deformable objects, liquids, and things like that. And I think today he's gonna give us an overview of his most recent work in that area. So I'm really looking forward to that. Go ahead, David.
Great. Thank you so much for the very kind introduction. Of course, I'm a huge fan of Dieter's work as well. And thank you, everyone, for having me. So today I'm going to talk about my work on perceptual robot learning. And so what is a robot? A robot consists of a perception system that processes sensor inputs and tries to estimate the state of the environment, and a planning system that takes this estimated state and tries to estimate what actions the robot should perform to achieve a given task. And typically we divide researchers in the same way. We have vision researchers that work on the perception side and robotics researchers that work on the planning side. And the question I'd like to ask is, can we build a better system by thinking about these parts together as perceptual robotics researchers? Now, to clarify, I'm not proposing that we merge perception and planning into a single end-to-end black box. I'm just proposing that we should think about perception and planning at the same time when designing the robot system. So when I discuss this idea, sometimes people say, well, why can't roboticists just use the output of a computer vision method? And to understand, let's look at what computer vision methods typically produce. Here's an example output where the method is detecting or segmenting objects in an image. And so the goal of computer vision is to understand what is in an image. On the other hand, the goal of robotics is to understand what will happen if a robot interacts with its environment. So if this robot were to take some action to interact with this towel, what would be the end effect? And the robot can then use this prediction to figure out what actions it should take to achieve a task. And so roboticists tend to have different goals from computer vision researchers. And thus we need to develop new perception and planning methods to meet the needs of a robot system that must both perceive and act. So how do we bridge this gap between perception and planning? For example, if we have this crumpled towel, how should a robot interact with it to achieve a given task? And specifically, how should we represent this object? There's different types of representations that might be possible, and they have different trade-offs in terms of how easily the robot can infer them from its observations or interaction with the environment, and how suitable they are for the task. So my goal is to learn to manipulate novel, perceptually challenging, and deformable objects, and I believe that this requires rethinking robot perception and planning algorithms to handle these types of objects and manipulation tasks. So what can we achieve with this perspective of perceptual robot learning? Here's a few examples of things that we've been able to achieve in our group. So you can see we're interacting with cloth, transparent and reflective objects, and other kind of unusual objects. And so I'll discuss today a few of the directions along these lines that we've been exploring. So I'm going to start by talking about a benchmark that we've developed for deformable object manipulation. This project was led by my student Xingyu Lin. So deformable objects are very important for many applications, such as the ones that you see here, but there's many others as well. But they're also very challenging for robots to manipulate. And this is for a number of reasons. First is their high dimensional state representation. So as opposed to rigid objects that can be represented by their 6-soft pose, deformable objects have a near infinite degree of freedom. They also have very complex dynamics, and they have self-occlusions. When they're in a crumpled state, you can't see the full object, and so this creates difficulties for estimating the state of the object. There's some work that's been done in this area of deformable object manipulation, but most of the papers evaluate on different tasks with different simulators and robot setups, and this makes it hard to compare algorithms to see if we're really making progress on these tasks. So to address these challenges, we developed a benchmark known as SoftGym, which is a set of environments built on top of the NVIDIA Flex simulator. So thank you to all of those of you out there with connections to NVIDIA. And so in this benchmark, we have a set of different tasks with deformable object manipulation, transporting water, pouring liquid into a cup, straightening rope, folding a flat cloth, spreading a crumpled cloth, and dropping a cloth in a way that hopefully ends up flat on the floor. And SoftGym is actually already being used by the community, even outside of our group. Here's 2 papers that use SoftGym that I really like. And so we'd encourage you to check it out as well if you're interested in this area. And using this set of environments, we were able to benchmark state-of-the-art deep reinforcement learning algorithms. So here with this black line, we're showing the performance of a dynamics oracle. So this is a method that assumes access to the ground truth state and ground truth dynamics of the environment and runs the cross-entropy method for planning. So the robot typically doesn't have access to the ground truth state or dynamics. And so this presents something of an upper bound of what you might expect a good method to be able to achieve. And here you can see the performance of different state-of-the-art deep reinforcement learning methods. I'm not going to go through each of these methods today, but the main thing I want you to notice is that if you look at these two tasks, spreading a crumpled cloth or folding a cloth, you can see that there's a large gap between the performance of the best deep reinforcement learning method today and what could be achieved. And so we're going to be focusing on those 2 tasks for the work that we'll describe next. One thing that we were wondering is why does deep reinforcement learning perform so poorly on these tasks? So in order to dive into that question, let's get a quick overview of how deep reinforcement learning methods typically represent objects. So typically they would take some image, compress the image to a Latent vector, and then pass a Latent vector through a policy to output robot actions, or input that Latent vector to a dynamics model together with a representation of the robot action, and then predict the next latent state of what will happen after the robot takes this action. And these methods are called model-free and model-based RL, respectively. And so one thing you might wonder, looking at this, is what does this latent vector actually capture about the observation, and is this latent representation sufficient for my task? Now, usually that's a very hard question to answer, but there is one set of methods in which we can gain a little bit more insight, and that's methods that do planning in latent space. So these methods would encode the observation into a latent vector, and then roll out a sequence of actions in latent space. So they use a latent dynamics model to make latent predictions, and then use a latent reward function to score this action sequence. You can then score different possible action sequences based on the latent predictions, and choose the action sequence that has the highest score according to these predictions. So let's see how this works. So here we're running PlanNat, which at the time of the paper was a state-of-the-art method that does planning in latent space, and it's trying to pour liquid without spilling. And here you can see what's happened. If and it's actually spilled many droplets of water outside of the cup while attempting to pour the liquid. Here's the droplets of water in case they're hard to see. And now we can look at what was the plan? What did it think was going to happen? And here you can see a visualization of the plan of what it thought would happen if it took these actions. You can see in its plan, it doesn't have any spilled droplets of water. And that actually makes sense if you think about it, because the spilled droplets of water take up only a very small number of pixels in the image. And so they don't matter that much in terms of the reconstruction loss. And they're also extremely hard to predict exactly where they're going to be. So combining those two aspects, small pixels, hard to predict, the easiest thing to do for the network is just to ignore them. Of course, for us, that's not very good because it's spilling liquid. Here's another example where the robot is trying to spread a crumpled cloth. And here you can see below its plan. So you can see in the actual execution on top, the cloth is very wrinkled. But in the plan, it imagines just this big orange blob, which is kind of the same phenomenon. The wrinkles in the cloth take up only a very small number of pixels, and it's very hard to predict exactly where the wrinkles will be. So the easiest thing for the network to do is just to ignore them. Now, you might see this, and if you're, kind of a diehard deep learning person, you would say, well, wait a second, can't we just use a larger Latent vector? So yes, I mean, that's basically true. You can essentially train this with a larger Latent vector, train it for a lot longer, and I'm sure eventually you could get this to work. Archimedes once said something similar. He said, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. His lesser well-known brother, R.L. Medes, once said, give me a large enough Latent vector and enough computation, and I can memorize any training set. Both of these statements are technically true, but not terribly useful for practical applications. And so, yes, with a large enough Latent vector and enough computation, we could probably get these tasks to work. But as we'll show shortly, we can learn much more efficiently by encoding some environmental structure into the representation that we use for these tasks. Okay, so wrapping up this section, we have this new benchmark for deformable object manipulation known as SoftGEM. It allows researchers easily develop new methods, and we demonstrate that deformable objects present a large challenge for state-of-the-art deep reinforcement learning. So that leads us to the next question, which is how should we actually represent cloth in order to do this task of smoothing a crumpled cloth? And particularly, we're going to explore the approach of learning a dynamics model. So meaning we want to be able to predict what will happen after a robot takes actions to this cloth. So this is a project that was led by my students Xingyu and Yufei. And the first approach that's the most common is the one that we discussed already, which is to compress the image to a Latent vector and then combine that with robot actions through a Latent dynamics model to make a latent prediction. And we already discussed how such an approach lacks environmental structure, which can make generalization difficult. Another approach, which works a little bit better, is to learn a pixel dynamics model. So these methods would predict an image of what the image would look like after the robot takes a certain action. This is an approach that was pursued by Ken Goldberg's group at Berkeley, including Daniel Seda, who's now doing a postdoc in my lab, so look out for him next year. And so this approach works a little bit better because it helps capture the 2D spatial structure in the image, but pixel dynamics might not sufficiently capture the underlying physics of the cloth. So we're going to take a different approach, which is to learn a graph dynamics model. So given a point cloud observation of the cloth, we're going to try to estimate a mesh of the cloth. We will then use a graph neural network dynamics model to predict how this mesh will deform in the next time step. So a mesh is a pretty natural model to represent a cloth. It's often in the graphics community because a cloth can be modeled by a set of points connected by springs, which are kind of the nodes of the mesh. And you can represent other forces on the cloth as edges or node potentials. But there's some challenges to representing a cloth with a mesh. So the first is that we don't get to see how the points are connected on the underlying cloth mesh in our observations. We just see a point cloud, but we don't know how these points are connected to each other in the underlying mesh structure. But there's another challenge, which is that we can't even see most of the points due to self-occlusion. So in this example with a crumbled cloth, you can only see points that are visible from the exterior, but not what's folded underneath. And so how should we handle occlusions? Well, maybe the best way is if we could estimate a distribution over the full configuration of the cloth, including uncertainty over the occluded regions. And we're currently pursuing an approach along these lines. But in this project, we want to make just a very simple point, which is that combining a graph dynamics model with a very simple approach for occlusions is still significantly better than using either pixel dynamics or latent vector dynamics or model-free policy. And so what is this simple approach for occlusions? So first, what we're going to do is learn to estimate how the visible points are connected. So in this example on the left, you can see that these pair of points are directly connected on the underlying cloth mesh, whereas this pair of points are not directly connected on the underlying mesh. They're just near each other because of the way that the cloth is folded. Does everyone see that? Please, I guess, nod your head if that, yeah, okay. So I guess at least some people are nodding, and great, thank you for the feedback. Cool, so we're gonna make a graph based on the estimated connectivity of the visible points. So here's kind of a cartoon illustration of what that looks like. And we call this a visible connectivity graph. And we're gonna learn a dynamics model just over this graph of visible points. So we call the visible connectivity dynamics, or VCD, and the dynamics has to somehow implicitly take into account partial observability because it's not being explicitly modeled in this approach. So here's an overview of how this works. We start with an observation from which we create a voxelized point cloud, and then we're going to connect all nearby points by edges, and then we're going to use a graph neural network to predict which edges are connected on the underlying cloth mesh. And then we will input this estimated mesh into a dynamics graph neural network, which will predict how the mesh will change in the next time step. And then we can input that prediction back into our dynamics model to make predictions over multiple time steps. So kind of digging into each of these parts. So the first part is to predict which points are connected on the underlying cloth mesh. So we input this graph where we've just connected all nearby points with edges. And then we're going to do the standard graph neural network thing, which is we encode each node and edge as a latent vector. We pass messages back and forth between nodes to edges, edges back to nodes, back and forth. And then finally, we're going to decode, which means we're going to make a prediction on each edge, which is a number between 0 and 1, which is our estimate of whether this edge is an edge on the underlying cloth mesh or not. So it's basically a classification task per edge of whether that edge is an edge on the underlying cloth mesh. Okay, so now we have our estimated mesh edges, and then we'll input that to the dynamics graph neural network, and along with the original graph where we've connected all nearby points by edges. And the dynamics graph neural network has a similar structure. You encode the nodes and edges, pass messages back and forth, and then decode. And in this case, the output is a prediction per node, which is the estimated acceleration of that node of how we predict that the node will move in response to the robot action. So that's our structure. And we're going to use this dynamics model to do planning. So we, in our paper, do this for both smoothing and folding. Here I'm focusing mostly on the smoothing task. For the smoothing task, we define a reward function, which is the covered area in a top-down view of the cloth. So we imagine a sphere on each node in the estimated mesh, and then we project these spheres down into a plane, and we look at the total covered area of all of these projected spheres, and that's the reward. So our objective is to maximize this total covered area. For planning, we use the simplest planning method that you can come up with, which is simple random shooting, which is that we sample and pick and place actions. We simulate the effect of each action using our mesh dynamics model. Then we score each action according to this predicted reward, and we choose the action with the highest predicted reward. So there's many more sophisticated planning methods that you can use. This is one of the simplest ones, but we use it just because the point of this project is that a graph dynamics model combined with a very simple approach for handling occlusions and a very simple approach for planning is still much better than using pixel dynamics or lane vector dynamics or a model-free policy. Okay, so we train this in SoftGym that we described earlier. We train it on just 2,000 random pick and place actions. And in comparison, all the baselines are trained on over 100,000 pick and place actions. So much more data than we use to train our method. And we use a voxelized point cloud as the input to our graph dynamics model, which allows us to easily transfer from simulation to the real world because we voxelize the point cloud the same way in simulation and the real world. So the input to our network looks pretty much identical in both cases. And we train in simulation on just one simulated cloth, which is a square towel. And we train just one network, one set of weights, and we evaluate it in the real world on a cotton square cloth, a silk square cloth, and a cotton t-shirt. And here you can see the results. So on the left is the actions that our robot is taking to try to unfold this crumpled cloth. On the bottom right is the mesh dynamics. So you can see the estimated cloth mesh as well as a prediction of how this mesh will deform in response to the action that the robot has planned to do. And on the top right, you can see some of the actions that we are evaluating. So each arrow is showing the pick point and the place point, and the color of the arrow indicates how good we think that action would be. So green means we think the action will be really good. Red means not as good. And so here you can see our method is able to generalize the different cloth materials and shapes, even though it's never seen t-shirts before. It was trained just on a square towel in simulation, but it's able to generalize the different shapes reasonably well. Yes.
Can I ask a quick question?
Yeah, sure.
So you indicated that you're only computing that graph at t=0, right? But the underlying structure changes as things get uncovered, and so you might have to insert nodes and things get connected that were not connected, things like that. Have you considered updating that?
Yeah, so basically what we mean by t=0 is within a single pick and place action, we look at the cloth, we've estimated the graph, and then we make a prediction holding the structure fixed but deforming the position of the nodes. And then after the pick and place action, we move the gripper out of the way, look at the cloth again, and re-estimate the mesh structure. Yeah, so we divide up a single pick and place action into many small time steps, and that's what I meant. Yeah. Thanks for that clarification. Yeah, great catch. Cool. So here's more examples of us uncrumpling 24 different cloth configurations, and in the end, they all end up reasonably flat. And next, I'll show the quantitative analysis. So in this case, the x-axis is the number of pick and place actions that each method is allowed to perform. The y-axis is the normalized improvement. So 0 means we didn't make any changes to the cloth from its initial state, and 1 means it's perfectly flat. So here you can see the performance of a model-free policy. Here's the performance of a latent vector dynamics model. Here is a pixel dynamics model, and here's the performance of our method. So you can see that our method is able to much more quickly find the actions to flatten this square cloth. And so we train all these methods and test them on square cloth in this case. And here you can see the performance if you test them on rectangular cloth or t-shirt. And you can see that our method is able to generalize to novel cloth shapes much better than the previous approaches. So in conclusion, we estimate the connectivity of the visible part of the cloth. We learn a mesh-based dynamics model, and we perform zero-shot material transfer for cloth smoothing of different shapes and materials. So I can pause briefly in case there are any quick questions at this point. Otherwise, I'll move on.
So it seems that actions you sample, they all go from sort of the edge of the class towards the outside area. That's is there something to do with the sampling, or is that important?
Cool, good question. Hi, Wentel, by the way. Yeah, so we do bias our sampling such that the place point is always off the cloth, which is probably a good bias for the task of unfolding. But we, use yeah, it's still I believe we use that same heuristic for the baselines as well. So, but yeah, it definitely helps to reduce the search space because we are doing a search over many cloth actions. So, so yeah, biasing it towards reasonable actions does help speed things up. Yeah, great observation. Cool. Okay, so that was learning a dynamics model for cloth manipulation. And next I'm going to talk about our project on how we learn to fold cloth, which is work done by my students, Thomas and Sujay. And so for this task, we've defined this task by a series of sub-goals that we are hand defining and inputting to our policy. And our policy is going to be a goal condition policy that takes as input the current observation and one of the sub-goals and tries to estimate what actions the robot should take to do the folding task. And we want also to sometimes use bimanual or single arm manipulation depending on the task. So how would we approach this? Well, the most common approach in previous work of reinforcement learning would input the observation and the goal both to a policy and have the policy output robot actions. What works, this in our experience doesn't actually work very well. What works a little bit better is to separately output the pick points and the place points as a heat map. But even this doesn't work as well as we would like. And that's because the policy in this case has to jointly reason about the relationship between the observation and the goal, and also where the robot needs to grasp to achieve that goal. So our insight is that we should first reason about the desired object motion, which means how all the points in the observation should move in order to achieve the goal. And then we can reason about the desired robot actions, which is how the robot should move the cloth in order to enable it to achieve the desired cloth motion. So let's kind of dig into how that works. So the first thing we're going to do is estimate the correspondence between the observation and the goal, which means that for each point in the observation, we're going to predict a vector of where that point has moved to in the goal. And here we've divided the task up into sub-goals. Each sub-goal is just one action away from the previous step. And so we then train this in simulation where we have the ground truth, which gives us all of the correspondences between the observation and the goal. And so we're going to input the observation and goal into a flow network, which is going to estimate this image of correspondences. For each point in the observation, we're going to predict where that point has moved to in the goal. So we estimate this 2D vector for every point. The flow network that we use is similar to architectures that are used for optical flow tasks in computer vision, which try to predict where each point in a video frame has moved to in the next video frame, except we're using it for this task of estimating correspondences between an observation and a goal. And we train this in simulation with the ground truth. Okay, so now we've estimated this flow image, which is an image of correspondences. And next we're going to input that to a PickNet, which we've trained to output the locations of where the robot should pick the cloth to move it in a way that enables it to achieve this set of motions indicated by the flow image. And then we're just going to query the flow at the pick points to find the place points. So to explain what that means, suppose this is the observation and the goal, and here is the set of estimated flows. And now we're going to, let's say we've output these 2 points as the pick points. And now we query the flow, which means we just follow these flow vectors to the end and find the endpoints. And those are the place points where we're going to place the cloth. Okay, so I mentioned earlier that you want to switch between single arm and dual arm actions. That's pretty easy to do actually, because in this case, since the actions are just continuous, pick and place points at the end. If the pick points are within a certain threshold, then we'll merge them together into a single action. And if not, then we'll keep them as two separate robot actions with two arms. The next question that we look at is, how do we decide when to progress to the next subgoal? And for this, we use flow as well. So we'll compute the flow magnitude to the current subgoal, and we'll progress to the next subgoal when the average flow magnitude to the current subgoal is less than a given threshold. So kind of to summarize, we take advantage of this idea of flow in three ways in this project. The first is explicitly reasoning about the relationship between the observation and the goal to create this flow image. The second is that we determine the place points by querying the flow at the location of the pick points. And the third is that we use the flow magnitude to decide when to progress to the next subgoal. As before, we train this in SoftGym and transfer it to the real world. We're going to train it with depth images as input, so SimTrial transfer is pretty easy. And so to review the main point here, unlike previous work that directly outputs robot actions or directly outputs pick and place points, we're going to first infer the desired object motion, meaning how the cloth, all of the cloth points should move, and then we're going to reason about the desired robot actions to achieve that object motion. So here's some videos showing our performance. So on the top left inset is the goal that we're trying to achieve, which is input to our network as a sequence of subgoals. And here you can see the robot is able to perform each of the folding tasks, sometimes using two arms, sometimes using just one arm, depending on what's needed to achieve that task. So I'll sort of skip forward. Here you can see the top row is all of the goals that we were trying to achieve, and the bottom row is what the robot achieved. And so you can see there's generally a pretty good agreement between the what we achieved and the goal. We also, in this case, are able to generalize to t-shirts as well, even though it was just trained on a square cloth. And this generalization basically comes from the generalization of the flow network. So in the computer vision community, people have shown that optical flow networks for video tracking are able to generalize very well to novel videos, even if they're just trained on, for example, there's a common data set of a video of flying chairs. And from training on that, they're able to actually generalize to all sorts of random videos. And so that same generalization of flow is what we're taking advantage of here. In terms of quantitative performance, so the y-axis here is the average particle position error. So lower is more accurate. And the x-axis is the inference time. So left is faster. And so you can see our method has a really good combination of better performance in the previous methods, but also much faster than some of the competing approaches as well. Here you can see some results in simulation, which actually match very well between the goals on the right and what we achieved on the left. So the biggest gap is probably in the SimTrial transfer. And here on the right, you can see the qualitative performance of one of the baselines in simulation. And so you can see that qualitatively, this baseline performs much worse. And so the difference in performance is not just some numbers on the graph, but you can see that there's a qualitative difference between our method on the left and the baseline on the right. Okay, so in conclusion of this section, we have a novel flow-based approach to bimanual goal condition cloth manipulation, where we explicitly reason about desired object motion, and then we infer the robot motion to achieve that object motion. And we use that idea to successfully perform cloth folding in the real world. Okay, so that was cloth folding. And we actually applied the same idea to the task of articulated object manipulation. I'm just going to very briefly sort of show a teaser about this work because it's kind of ongoing, but recall the insight from the last project where we were inferring the object motion first and then the robot actions. And so can we apply this idea to learn to articulate unseen objects? So here's a number of objects in the real world, and we don't necessarily know their category, and we haven't seen these particular objects before. How can we learn to articulate or specifically to open them? So what we're going to do is the following. For each object, we're going to first infer the desired object motion. And for the task of opening, what that means is for every point on the object in the 3D point cloud, we're going to predict a vector, which is how would that point move instantaneously if I were to open this object by a small amount. And so this is essentially predicting the affordance of this object on a per point level. And then we can infer the desired robot actions to achieve this affordance, which is actually pretty easy. Essentially what we can do, just do motion planning. And so essentially we want to grasp a point that has a large estimated flow vector and is relatively flat and easy to grasp with a suction gripper. And then we can move that point in the direction of the estimated flow vector. And so that's our method. And we're able to use that method to articulate all of these objects, some of which are novel categories, all of which we haven't seen before. We train only in sim and then transfer to the real world, again, just using point clouds. So the main insight here as well is to first infer the desired object motion and then for the desired robot actions. You can see that this insight is sort of generalizable to different kind of tasks. Okay, and so I guess the last project that I'm going to talk to you about today is this task of cloth grasping. And this is work done by my students, Aurora and Thomas. So the task here is to try to grasp a true edge or corner of the cloth. And by true edge, I mean, if the cloth were unfolded, what would you consider to be an edge of the cloth? It's sort of these edges here shown in green, as opposed to these other things shown in red, which are basically just folds or wrinkles of the cloth. They sort of appear as edges from this perspective, but that's just because of the way that the cloth is folded. And we want to be able to grasp the true edges in order to perform downstream cloth manipulation tasks like folding. So how would we do this? The approach that we're going to take is essentially semantic segmentation. So we're going to input a depth image to a segmentation network, and we're going to estimate heat maps over the pixel locations, classifying them as corners or edges, or neither. And we get ground truth for this using a colored cloth. So we've colored the corners and edges, but our network doesn't see the color. It only sees the depth image as input. And so we can use this as the loss and then generalize to other cloths. Now, so far that might sound pretty reasonable, but there's kind of an issue that comes in when you try to actually use this approach for manipulation, which is, let's say we're trying to grasp the cloth edge. And so here's maybe a predicted segmentation of the edges. And but the question is, we want to know, how should we approach the edge? Should we approach it from this direction or from this other direction? And just knowing where the edge is in terms of a segmentation is not sufficient to determine that. So to solve this problem, we're going to apply the trick again, which is we're going to actually also color the inner edges, and then we'll output the outer edges as well as the inner edges, which will tell us the directionality of the edge and help us determine how to grasp the edge of the cloth. Okay, so let's kind of dig in on how that actually works. Suppose this is the estimated segmentation of the cloth, and so we've estimated the corners in blue, the outer edges in yellow, and the inner edges in green. And so now let's zoom in on this part of the cloth. And so question is, where should we grasp the cloth? Well, we'll grasp it at the outer edge, for example, here. And then the next question is, in which direction should we grasp it? And basically, we want to grasp it in the direction from an outer edge to an inner edge, kind of like this, from yellow to green. Now, the problem is, what about these points here? So these are arrows that point from an outer edge to an inner edge, but they don't point from the outer edge to the corresponding inner edge. They point to kind of just another inner edge that's nearby because of the way the cloth is folded. So how do we handle that? The way we handle it is by reasoning about directional variation. So if we were to take a neighborhood around this point here, and then compute the nearest inner edge to each point in this neighborhood, we'll see arrows going in many different directions. As opposed to if we take a neighborhood around this point and compute the nearest inner edge to each point in this neighborhood, all the inner edges are pointing in the same direction. And so we can use this as a measure of directional uncertainty. So we want to basically grasp at a point that has low directional uncertainty that we also estimate to be an outer edge. And we train this on just 8 minutes of video. Kind of looks like this. It's pretty easy to collect. And here you can see the results. So basically we're observing this crumpled cloth. We're segmenting it, estimating outer edges, inner edges, the direction from the outer edge to inner edge, and then also directional uncertainty, and using that to determine how to grasp the cloth at either a corner or an edge, depending on the task. So here you can see that we're able to do this pretty robustly in different cloth configurations. And we're also able to generalize to different textures and materials. The texture is easy because we don't see the texture, we just use depth as input. And the size we're able to generalize because we use a fully convolutional network that generalizes pretty well to different cloth sizes. We compare it to different baselines, and we do an ablation, and we show that if we don't reason about the direction in which we should grasp, then our grasping success rate drops pretty significantly. And if we don't reason about directional uncertainty, we also see a large drop in grasping success. So both of those components are actually very important for the success of the downstream manipulation task. So to summarize this section, our method distinguishes the true edges of the cloth from wrinkles and folds. We select a grasp based on the estimated directional uncertainty, and we thereby achieve robust grasping of crumpled cloth. Okay, so I started the talk by asking this question, which is how do we bridge the gap between perception and planning? And so let's see what insights do we learn from these 3 projects that we talked about today. So in the first project, we're using a graph to reason about the relationship between different object parts. In the second project, we're reasoning explicitly about the relationship between the current state and the goal. And in the third project, we're reasoning about the relationship between the outer and the inner edge. So what we see that all of these 3 projects have in common is reasoning about relationships. I think that relationships are extremely important for many robotics tasks, and I think they don't take a high enough priority in machine learning in general. So I think in the future, we should probably focus more on reasoning about relationships for robotics. So where do we go from here? So as I mentioned at the beginning, I'm interested in representation learning for deformable object manipulation. There's many types of deformable objects beyond the ones that we saw in this talk. I'm also interested in manipulating other kind of non-standard objects. Here are some videos of us grasping piles of transparent and specular objects, or pouring transparent liquids into transparent cups. I also think that tactile sensing is increasingly important for fine-grained manipulation tasks, especially things like cloth, where the state of the cloth is not necessarily easy to infer just from visual observations due to occlusions or subtle details of the cloth that are important. And so we're exploring the use of tactile sensing as an additional input modality. And in the future, I'm interested in reasoning also about object interactions. So for example, multi-object tasks, like reasoning about the relationship between a lid and a jar, reasoning about the relationship between tools in an object, and how can we use the extrinsic environment to achieve a task. So all these examples involve reasoning about the interactions between different objects. I'm also interested in learning from visual demonstrations. So one of the directions we're exploring next is, can we combine a large number of unlabeled video from which we can learn a visual representation and maybe a weak action prior from watching the human hands, and combine that with a small number of human demonstrations, which gives us a robot action prior, and maybe a very small amount of robot interactions. And in order to put this together, figure out how to put these things together to actually achieve a task. So I'll kind of wrap up here. These are the different projects that I showed today. I only had time to talk about these three in detail, but feel free to ask me about the others if you're interested. I couldn't have done this without the help of my students who I've had the great pleasure of working with, who did all the work for these projects. And the other direction that I didn't get to dive into much today that I've also been exploring is self-supervised learning for autonomous driving. So if we can collect a large data set for autonomous driving, can we remove the need for human labeling? So I've explored this direction for various perceptual tasks for self-supervised learning for autonomous driving. And we've also explored active perception using a novel sensor called a light curtain that you have to decide where you want to sense. And this is, again, done with the support of my generous sponsors and the fabulous students who worked on these directions as well. So I'd again like to acknowledge the terrific students that I was able to work with and my generous sponsors. And I can end here and take any questions that you might have.
Great, thank you so much. Questions?
I have one. Hi, David. This is Karthik here. Thanks for the excellent talk. Can you just give me like maybe your thoughts on like having multiple deformable objects in a scene? If so, how can one approach that problem?
Yeah, that's a great question. So in general, I guess for reasoning about multiple objects, I still like the idea of using a graph-based representation. Essentially, different types of edges in the graph can represent different types of things. So in some way, if you think back to the graph dynamics model that we were working with, I'll kind of jump back to the slide actually just to kind of remind you. So essentially, we have two types of edges, right? One is between different parts of the cloth that are connected on the underlying mesh. And the other is different parts of the cloth that are kind of just near each other because of the way the cloth is folded. And those are also important because they, one part of the cloth can still apply a force to another part of the cloth if you kind of push it. And you kind of have similar types of force interactions between multiple cloths or multiple objects if they're near each other. And so those can also be represented as another kind of edge. So I guess I'm not necessarily saying that this exact form of the graph is what you can use to solve all tasks. But I guess I do think that graphs in general are a good generic representation for representing interactions both between different parts of one object and also between multiple objects.
Thank you.
Yeah, great question.
I have two questions actually, if there's time, and we'll see. The first one is on when you use the flow networks, right? Typically flow usually is being used like where you actually can do the data association between the two, let's say, images or so, right? But in your case, I can imagine when you're folding a cloth, especially if you do it, is that also with visual information here?
It's depth images.
Oh, depth only, okay. So you're not able to consider, let's say, the color itself in the folding process then.
Yeah. So that.
Yeah. Go ahead.
Right. So yeah, that's a great point. Is should we consider color? And there's definitely trade-offs there. Mm-hmm. The biggest reason that we didn't use color is that, I mean, if you look at these pictures, they're very cartoon looking. This looks nothing like kind of what like a real cloth looks like. I guess this is the real cloth image, right? And so you wouldn't really expect this to transfer well without some intensive, I don't know, domain randomization or something. But I guess to avoid that, we just use depth images because we find that transfer is easier. Now, I kind of agree, though, that in some sense, you might think, okay, maybe the texture on the cloth can help you do the correspondence problem. in this case, it also would be a little bit tricky. Like if you look at just this example, we're looking at one side of the cloth here in yellow, and then when it folds, you get the other side in blue. So if the two sides of the cloth have different textures on them, then that actually is still not a super reliable cue for correspondences either. And sometimes, you know, even if you say you see a pattern on the cloth that has edges on it, you might get confused about whether that's an actual edge, like this kind of edge here between the blue and the yellow, or just an edge in the texture. So that's kind of the reason we didn't use that. But there are definitely cases when it could be helpful.
Yeah, that's what I was also getting at, the difficulty that you can't actually necessarily do explicit flow because things look totally different from the other side, right?
Right. But from depth, I think, I mean, I guess it's not explicit flow. Yeah, I guess if you mean by explicit flow, sort of like looking for something of the same visual appearance. Yeah, it's not exactly doing that. It's more like it's trained to learn that when you see this and this, well, I guess what's happened is probably all these points have moved over there. Unlike the way you would do it by looking at these two examples.
So maybe there's some connections even to, you know, the transporter network stuff, right? Where they're also kind of moving things. They do it for individual grasp or so, but there's also this notion of from here to there. And in your case, I guess it's also, you could view it as flow, but maybe you could even view it as kind of actions, right? Like where something should move.
Right. Yeah. So there's definitely a relationship there of figuring out kind of like correspondences, and they do it in a way of kind of convolving a template with different locations. And I guess we sort of train something to estimate the correspondences directly. One thing that we were thinking about here is that's kind of related to that concept is if you look at the like certain flow architectures like FlowNet 2, they actually do this iterative procedure where they warp the image based on the estimated flow, and then they map the warped image to the goal in an iterative way. And I think that approach actually would probably have problems here, where, you know, if you're sort of matching two video frames with pixels and colors, warping can probably get them to align. But in this case, you're actually folding something. So I think sort of like imagining a warped image might not work as well. And I guess maybe for sort of similar reasons, we actually tried transporter nets on this problem, and it didn't work directly because it's not just, you know, sort of a translation and rotation. There's actually some folding that changes the structure, and there's also lots of symmetries that confuse the network too. So that's, I guess, where we went for a little bit of a different approach. And also maybe just put a shout out to Raft3D, which is from Princeton, that I think is, in my mind, a really solid approach for correspondences, but we weren't able to fully integrate that into our system.
That makes sense. Another question, maybe someone else wants to chime in too, but the question was, so you showed these three pieces and they're all kind of, you mentioned also related to somewhat kind of relationships between things in your input data, let's say, or your representation. But in the end, you had to give it a lot of kind of still, let's say, manually designed guidance, right? For example, in this case, right? Like, what do you even mean by edges and inner edges, outer edges, and things like that? So the representation did not emerge from the task, but you still kind of had to put in a lot of effort on choosing that representation that was good for the task, right? Do you think there's any chance of, at some point, maybe with more data, or I don't know, to get somewhere where a joint representation could just come out of these representations or the training data?
Yeah, that's a great question. So first, actually, I kind of just want to give a quick answer on the philosophical side for students who are attending this talk. Philosophically, I think there's two approaches to research. one approach that some people take is to say, let's start with a representation that we think is super general and apply it to our problem, and maybe it'll work. And then I typically take the opposite approach of, let's solve the problem that we're currently solving, but let's work on a sequence of increasingly difficult problems. And in order to solve each one, you need a kind of more general representation to solve the more complex problem. And eventually we get to the general representation that you're kind of hoping for. So that's just philosophical. In the direct answer to your question, yeah, I guess in my mind, of these three, the one on the right is the most where you had to kind of hand design things. The one on the left and center, I guess, I think of as pushing towards this more general representation. Like, I think a graph itself can be used to model many things, many types of relationships. And so I guess, yeah, I think that with a diverse enough set of different types of objects and interactions like liquids, dough, things like that, we can learn to infer what kind of edges are needed for each task. And then in the center one, it's more on the policy side. And there, I think the representation is also pretty general. We showed it actually, or at least the insight, applying to articulated objects of reasoning about affordances, and then doing motion planning from there. So yeah, so I guess my hope is that these directions are already pushing towards that more general thing.
Yeah, no, and I fully agree with the dense flow that seems like a clearly a general representation for many things that involve some kind of motion, right? So that's really nice. And I like the overall project. I think it's very much also in spirit of a lot of work in general that's going on in robotics, right? Where we actually want to solve some tasks sometimes.
Right. Yeah, it's a fun field to do. Yeah.
Dave, thank you so much. That was really, really nice work. Really exciting stuff, and I'm sure everybody enjoyed it. And thanks everybody for coming, and have a good weekend.
Great. Thanks so much
for
having me.